Okay, calculus. We are headed into actually the last section in chapter 5, believe it or not. So I'm saying late next week we'll have to do a test. So Thursday, Friday-ish probably. We'll see. I'm thinking probably Friday, not Thursday, because, and maybe even the Monday of next week. We'll see how this goes, how you're doing with this. So far in this chapter, we've done composite functions, f of g, g of f. Then we did the chain rule. Then we did implicit differentiation, which I haven't gotten questions on that yet, but I think today is the day you're supposed to hand the homework in, so I just haven't gotten that, we haven't gotten that far yet. I kind of expect to be going over a little bit of that with you probably. But building on implicit differentiation is, where do you use that? How do you use that? How does that come into play in questions? So of course, the last section deals with the word problems that go with that. They're called related rate questions. They're very, very common to see in calculus, in physics. They're very common questions that you're going to get. So you really do need to know how to deal with them. The first example I'm going to do is not one that I would be expecting you to do on your own, because it deals with circles and you have to know things like the formula for the circumference of a circle and that kind of stuff, and I'm not going to go there. For related rate questions that I'm going to expect you to do on your own, most of the time it's going to be dealing with not most, all of the time, it's going to be dealing with right angled triangles. I'm going to do one that doesn't deal with right angled triangles just so you can see kind of how it would be applied. But we're going to do just that one. And again, it's not one I'm going to expect you to be able to replicate on your own, but it introduces the idea of how you would go about solving something like this. So in example number 1, in the related rates section, this is page 292. It says you have a bike and the bike tires have a radius of 35 centimeters. Welcome to physics class. If the bicycle moves forward at a speed of 6 meters per second, at what rate do the tires turn? Okay, so at what rate do the tires turn? That's what they're asking. Whenever you see that word rate, you really need to think derivative. Whenever you see the word rate, you really need to think derivative. So, I missed my podium. So here it says it's easiest to solve the problem by finding a relationship between the distance that the bike goes and the number of rotations that the tires do. Okay? So the rate of change of the distance with respect to time is the derivative, dx over dt. Okay? And the rate of change of the number of rotations with respect to time. So how many rotations does the tire do in a certain amount of time is going to be, we're going to call it dn for number of rotations over dt. Okay? So, first off, when the tire turns once, if a tire just goes around once, the distance that you travel, the distance that the bike goes forward, is the distance around the tire, right? Because if If you have your bike tire and it starts here and you travel a distance until that spot is back on the ground again, you've traveled one full circle of that tire. You've traveled the circumference of that tire. So if the circumference of the tire was 0.5 meter, you would go 0.5 meter forward in one tire rotation. Okay, that's what they're trying to say. So if that's true, okay, so if that's true, then when the tire turns once, the distance traveled by the bike would be 2 pi r, because that is the formula for the circumference of a circle. Okay, the distance around the outside of a circle. See why I said I wouldn't ask you to do this one on your own? I don't expect that the circumference of a circle is necessarily common knowledge. It might be, but I'm not going to assume it. Okay, so if the tire turns twice, then the bike travels 2 times 2 pi r. If the tire goes around 3 times, then the distance is 3 times 2 pi r. So if we want to talk about distance then, and they replace distance with the letter x. Distance is 2 pi r times the number of times that the tire goes around. Again, if it goes around 3 times, then it would be 2 pi r times 3. Since the radius of the tire is 35 centimeters, now here's a problem. The radius of the tire is in centimeters, the velocity is in meters. So we're going to change this to meters so that the measurements agree, okay? Since the radius of the tire is 0.35 meters, okay, then we can actually replace 2 times pi times 0.35 times n, because we know what r is. Now 2 times 0.35 is 0.7 pi times n. So all we did was simplify that a little bit. So distance, which they're calling x, is 0.7 n, okay? So it says we can differentiate this equation with respect to time to obtain the derivative. So whenever, I don't know how to say this, whenever we're doing related rates problems, your independent variable is always time, because how far you go depends on how long you travel, right? So your independent variable is always t for time, which means when you're doing the derivative, you're doing the derivative with respect to time. So if I want to find the derivative of x, I'm going to find the derivative of x with respect to time, okay? So the derivative of x is 1, but I have to say I took the derivative of x with respect to time. Now, over here, I'm going to do the derivative. So again, really, don't think of pi as a variable. It's not. It's a number, 3.14, whatever, right? So it's a number. So really what I'm doing, the variable is here. So I'm going to take my 1 down in front and multiply it by this, which means it's still going to be 0.7 pi. I'm going to decrease my exponent by 1, so that's nothing. So I don't have any n's left. But again, I have to say that I did the derivative of n with respect to time, okay? Now, remember, we're looking for at what rate do the tires turn. That is what dn over dt is. We're actually looking for what is dn over dt. That's what we're looking for. Now, distance is x. The derivative of x is dx over dt. So think back. What's the derivative of distance? The derivative of distance is velocity. So dx over dt is actually your velocity. So, do I have a velocity? It turns out I do. 6 meters per second. So I can actually replace dx over dt with 6, and then I have 0.7 pi times dn over dt. Now remember, dn over dt, the rate that the tires are turning, is what I want to find. So I'm just going to divide this by 0.7 pi, and that will get my dn over dt alone. And so I'm going to divide this side by 0.7 pi, and when I do that, I get 2.73, and so that is dn over dt. So what is that in real life? 2.73. It means that the tires turn 2.73 times per second, okay? So every second, that tire is going around 2.73 times if the person is going 6 meters per second. Some bikes actually have a little speedometer on them. That's actually what it measures, is how many times are the tires rotating, and it translates that into how fast you're going. Interesting little fact, my husband's car, when he bought it, had, I don't know, I think 20-inch tires on it. And so the speedometer, the thing that tells you in your car how fast you're going, was calibrated to the rotation when you have 20-inch tires on it. So it keeps track of how fast your tires are going around, and it translates that into kilometers per hour. So when my husband put his winter tires on, it was a whole lot cheaper to buy smaller tires. So he bought 18-inch tires for the car and put those on. As a result, his speedometer was off a little bit. It wasn't his true speed. So he would have to keep that in mind if he was traveling on the highway, because if it said he was going 120, he actually wasn't. He would be going a little bit off from that. Not a lot, but a little bit. It was enough to throw it off by a few kilometers per hour. And so he would just have to be aware of that. Because again, what the car does, it doesn't know how fast you're going. It knows how many times the tires are going around. And it translates that into how fast you're going. So if you change the size of the tires, you change how many times it's going around, and the car doesn't know what size tires are on it. And so it still does the math for 20-inch tires. So just a little, that's a real life place where that comes out. All right. So a couple of other examples. These next two examples are going to be examples that I would expect you to be able to do. We're skipping example 2, which talks about the expansion of the sun. The information in it's kind of interesting, but the math in it is it freaks people out. And so rather than freak you out, we're going to go over. Now, halfway down page 293, it says, when solving When solving related rate problems, it's helpful to apply this process. First, read the problem carefully, so that you understand what you're asked to determine. And so you saw me up here making lists and writing things out. I do that a lot. If you're in physics, you know I do that a lot. Identify the key pieces of information in the question. Draw a diagram if you find it helpful. Again, if you're in my physics class, this is second nature by now for you. Assign variables to the relevant quantities, and determine a relationship. And that's the important part, trying to figure out the relationship between all of this. And then you're able to solve. So example 3 is where I am headed. We're going to do example 3 and example 4, and that's all. again, there's one about a volcano erupting, but it has to do with a cone, and most of you don't know like the volume of a cone right off the top of your head. So I don't ask you to do that. So example 3, it says, as a simplified crankshaft, I don't know. Imagine a 5-meter rod sliding in a track that has a right angle bend in it. So I'd have to get my husband up here to explain what a crankshaft is, because I don't actually really know. But here's what I know. You've got a rod here, okay? And it slides up and down, okay? And there's a 90-degree bend here, okay? So here's the rod, and it's resting on this 90-degree frame, okay? So it's a track. It's a track. So it can slide up or it can slide down. It goes up and down, all right? I know that has something to do with a car, but I don't know what. The upper part of the track is vertical. Voila. The lower part of the track is horizontal. Voila. All right. And when the bottom of the rod is 3 meters from the bend in the track. So when this is 3 meters, it is slipping away from the bend at a rate of 20 centimeters per second. Now the jerks are, again, using different measurements, which is frustrating, to say the least. Okay. How fast is the top of the rod moving down the vertical part? So we're looking at the rate that the rod is sliding down this side. So if it's sliding out, this side's sliding down. How fast is it sliding down? When the bottom of the rod is 3 meters from the bend. Okay. So it's a 5-meter rod. So I know that that is 5 meters. Okay? And we want to know the rate that this is going down. So this is going across. I'm going to call this X. All right? Now this is the rate that this is going across. When you have a rate, that is dx over dt. It's the rate. This is the length. This is the distance, if you want. This is the rate. So it's the dx over dt. I know that that's 5. So we'll call it Z. You can call it R. You can call it H for hypotenuse. I don't care. I'm just calling it Z. And we don't know a Y. But we want to know the rate that it's going down. So we actually want to know dy over dt is what we really want to know. That's what we're looking for. We're looking for a rate. So it's got to be a something over something, and we're looking for the rate that it's sliding down the vertical part. The vertical part I'm going to label y, because that just makes sense. So we're looking for dy over dt. So here's what I know. I know that x squared plus y squared equals z squared. The Pythagorean theorem, right? I can figure out what y is because I know that x is 3. I know that z is 5. So 9 plus y squared is equal to 25. So y squared is equal to 16. So y is equal to 4. Aha, I have that. But I don't have a formula anywhere that has a dy over dt in it. I just don't have one. But here is what I know. know, okay? I know that it's a 5-meter rod. So no matter what, no matter how quickly this is moving, no matter like whether the rod is way up here so that the X is only 1 and Y is something else, this 5-meter rod is never changing length. The hypotenuse is not changing. It's a 5-meter rod, no matter what. So I could say that whatever X squared is plus whatever Y squared is has to equal 25. It has to equal 5 squared. So even if these measurements change, it still has to equal 25. All right. If, again, I don't have a dx over dt in there. I don't have a dy over dt there. But if I do the derivative of this, the derivative of x squared is 2x. But again, I have to say that I did the derivative of x with respect to time. Plus, if I take the derivative of y squared, that is 2y. But again, I have to say I did the derivative of y with respect to time, meaning time is the independent factor here, right? And the derivative of 25 is 0, and that was a z. So I could say I did the derivative of the z with respect to time. So the good news is that side's just 0. And if I wanted to, I could divide everything here by 2 because I have 2x dx over dt plus 2y dy over dt. So I could just divide this by 2, divide this by 2, and divide the 0 by 2 and get rid of the 2, but you don't actually have to. The only thing you really need to make sure of here is that we change either the meters into centimeters or the centimeters into meters. It doesn't matter. They change this. They change this. So if it's centimeters and we want it to be meters, there's 100 centimeters. So divide by 100, it would be 0.2 centimeters per second. Meters per second now. So that my units agree, meters and meters. So 2 times x is 3, times dx over dt. dx over dt is 0.2, plus 2 times y. We figured out that y was 4. We don't know what dy over dt is. That's what we want to know. And it equals 0. At this point, you should be able to solve it. 2 times 3 times 0.2 is 1.2 plus 8 dy over dt. And so I'm running out of space as usual. I miss my big giant boards. I won't know what to do if I ever get to go back to work. Is equal to 0. So 8 dy over dt is equal to negative 1.2. Divide this side by 8, divide this side by 8, and I get dy over dt is negative 0.15 meters per second. So, so if horizontally it is moving at, 20 centimeters per second, the top part is sliding down, hence the negative. That's what the negative means. It's sliding downward at 0.15 meters per second. So again, we use the Pythagorean theorem here in order to figure this out. All right. Neha, Grace, and Veronica, the next question is going to sound all too familiar. All right. So example number 4 at the bottom of page 295. In an automobile crash test, we've been talking about crashes in physics as well. 2 cars are approaching an intersection. Car A is traveling west and it's going 45 kilometers per hour. Wow, that's really badly done. So car A is going west at 45 kilometers per hour. That's a speed, right? I would label that as dx over dt personally, because again, that is a rate. It's how fast something is going. So dx over dt, again, x is distance over time, right? Distance kilometers over time hours, kilometers per hour. Whoops, helps if I stay on the same page to read the question. Car B is traveling south and it's going 60 kilometers per hour. So here's car B and it's going 60 kilometers per hour. Now I would call that dy over dt because it's vertical. The force of the impact is proportional to the rate of change of the distance between the 2 cars. In other words, how much force they're going to actually feel when they impact depends upon how far apart they are at any given moment until they hit. So it says, determine this rate when car A is 0.6 kilometers. That's a distance, so that's just plain old x. And car B is 0.8 kilometers, so that's just a y. Okay? From the intersection point. Okay. So, luckily, the units actually agree this time, kilometers and kilometers, so I don't have to switch anything, which is lovely. Now, I can figure out a z on this one because, again, I can do Pythagorean theorem. X squared plus y squared equals z squared. So 0.6 squared plus 0.8 squared equals z squared. And so z ends up being 1. Okay? So, since the cars are moving towards one another, this car is going west, it's headed in that direction. Think about a Cartesian plane. Think about an XY axis. Going this way is actually the negative direction. So I'm actually going to make the velocity negative. Sorry, I have a husband and a dog at my feet. He's trying to coax the dog to come to him and it's not going well. Just a sec. Wicket. Say hello. Say goodbye. All right. Sorry, a little drama at my feet. So once I figure out that that is 1, again, I know where I was. This is going in what would be considered the negative x direction, so I put a negative on it. This is headed downwards, which would be negative, so you could consider that negative as well. Okay? Now, what we're looking for, we have to decide what we're looking for because, hey, guess what? It looks like we have almost everything. Before we were looking for a dy over dt. We're actually not looking for that this time because the rate of change of the distance between the 2 cars. So as these cars come together, this Z is going to get smaller and smaller and smaller, right? Because the closer the cars get together, the shorter this is going. So what I actually want to know is, how quickly is that changing? I'm actually looking for dz over dt this time, the rate at which the distance between them is closing. So I have figured out pretty much everything I can figure out here. So I now need to have an equation that has all of those things in it. So this time, because I'm looking for dz over dt, and because this z can actually change, in the last one the rod was 5 meters long, it wasn't going to change length. The rod was a fixed length rod, it was 5 meters long, it was never going to change. It was basically a constant. And so we actually substituted the number in here. This time the z is constantly changing values. So we're not going to substitute a value in there to do the derivative. What we're going to do is we're going to do the derivative of x squared, which is 2x, and we're going to say we did that with respect to time, plus the derivative of y squared is 2y, and we're going to say we did that with respect to time, and we're going to do the same thing on the other side. The derivative of z squared is 2z, and we're going to say we did the derivative of z with respect to time. Again, because there's a 2 in front of every single piece, we could divide by 2, but you don't have to, okay? I'll just do it leaving it there, but I could have divided everything by 2. So 2 times x, x is 0.6 times dx over dt. Now remember, it's negative 45 plus 2 times y, my y is 0.8, dy over dt, which is 60, is equal to 2 times z, and our z right now is 1 because we're figuring out at this instant in time, and dz over dt, we don't actually know. That's what we're looking to find out. So 2 times 0.6 times 45, that is negative 54. 2 times 0.8 times, oh, that should be negative 60, times negative 60 is negative 96, is equal to 2 times dz over dt. So 54 and 96, that is negative 150, is 2 dz over dt. So divide both sides by 2. I get that dz over dt is negative 75 kilometers per hour. So again, what am I saying with that? I am saying that the distance between the two cars is decreasing. The distance between the two cars is decreasing because it's negative, at a rate of 75 kilometers per hour. So when they actually hit, even though this guy's only going 45 and this guy's only going 60, the impact is actually going to feel like a 75 kilometer an hour hit. So basically it's the same as if you drove your car into a brick wall going 75 kilometers per hour, is really what they're saying. So because part of this guy's velocity and part of this guy's velocity is going to go into the impact. Welcome to momentum. Welcome to physics. Those of you in physics, you can cry now. Okay. It all works together. So I'm going to put up some questions for you to do. It's the Easter weekend, so you can either do them today, which is Thursday. You can leave them till later. I'm going to be looking to see how you did by Tuesday. So we will see you next week. Again, we will have a test, I would say either Friday, or we may even push it off into the next week, depending upon how it's going for everyone. So again, just a real quick recap: composites, F of G, G of F, chain rule, implicit differentiation, and now related rates. I will put a few questions up for you to try. Not a ton, just a few. Okay? So have a good Easter weekend, and we'll see you. We'll talk to you. You'll see me. I probably won't see you, but we'll talk next week.